In the last video, we showed how we define this L1 space, which is a vector space, and it has a semi-norm on it. And in this video, I'm just going to briefly talk about what happens when you have a semi-norm on a vector space. And usually, a semi-norm is really close to a norm, and there's a really standard procedure of quotienting out the kernel of the semi-norm, and you'll get the normed vector space. Okay, so I'm going to briefly talk about how we do this general construction. And if you're actually interested, semi-norm is also related to something called a pseudo-metric. So if you just treat V as this vector space and you have some semi-norm, you can actually define a distance between x and y to be the norm of x minus y. Okay, this distance is just really similar to a metric, but their only difference is that the distance can be equal to 0, but x is not equal to y. Okay, so this is called a pseudo-metric, and something really similar happens for a pseudo-metric. So when you have a pseudo-metric, what you do is you can define an equivalence relation by saying x is equivalent to y if their distance is equal to 0, and you consider the equivalence class. Okay, so if you go back to your assignment number 2, I put a question on this pseudo-metric on all the measurable sets, and then you do the equivalence relation, and there you can actually get a metric space. Okay, so what we're going to do for the vector space here is really similar. Okay, so the only difference here is V is assumed to be a vector space, so I need the quotient to have a vector space structure as well. Okay. Anyway, so here let's talk about our proposition. So this is really standard, just works for any vector space with a semi-norm. Okay, so let's let this V and the semi-norm be as given. So if I let n to be all the f inside this vector space where the semi-norm of f equal to 0, okay, so then I have the following. So first of all, this n is a linear space, so it's a subspace of V. Okay, it's a subspace, so it's a linear subspace. And whenever you have a linear subspace, you can define the quotient vector space. Okay, so we can define the quotient, or you can just define the following. You say f is equivalent to g inside V if the f minus g is inside this space. That's exactly how I define the quotient vector space. Okay, so you consider all the equivalence class, which give you a vector space. So this is just all the equivalence class. Let's call it f tilde. Okay, so f tilde is just the equivalence class of f. Okay, sometimes you can just write f plus n because everything is linear. So f and g are equivalent if and only if f is g plus some n inside this curly n. Okay, so this is a vector space, and I actually want to show that this is a normed vector space. Okay, so I can define a norm on this. So let's abuse our notation a little bit. So I define the norm of an equivalence class just to be equals to the semi-norm f. Okay, so if I want to make it a little bit more clear, I should put a 0 in the semi-norm. So how about let's do that just to make it a little bit clear where I mean by a semi-norm. So here on the right hand side, I'm taking the f, the semi-norm of f, and I define it as the norm function of this equivalence class. Okay, so here f tilde is equal to f plus n. Okay, so it turns out then this new norm we defined, okay, is in fact a norm on this V quotient n. Okay, so it's going to be so V quotient n basically become a normed vector space. Okay, so let's prove this fact. Okay, so first of all, I want to show that n is indeed a vector space. And to show it's a vector space, I just need to show that if I take any f and g inside n, and if I take any lambda scalar inside here, everything is in real. Okay, so let's consider what happens to the f plus lambda g. Okay, I need to show that the semi-norm is still equal to 0. Okay, so V contains all the function with the semi-norm equal to 0. So I want to show this linear combination also have the semi-norm equal to 0. The semi-norm satisfies the triangle inequality, so I can break it into the semi-norm of f and the semi-norm of lambda g. And semi-norm also satisfy this the scalar. You can pull out the scalar, so you can do the lambda out, and then you do the semi-norm of g. And because f and g are inside this kernel or inside this space n, so the semi-norm of f and semi-norm of g are both equal to 0. So this is equal to 0. Okay. And well, I should say semi-norm is always non-negative. So because it's non-negative and it's less than equal to 0, so it's equal to 0, we have f plus lambda g is inside n. Okay. All right, so we now prove this basically shows n is a vector space. Okay, so now let's prove the quotient is a normed vector space. Okay. So first of all, whenever you define something on an equivalence class by just taking a representative, you need to show this is well defined. Okay. So why is this well defined? Well, let's say, suppose I have a different choice. So let's say this equivalence class, I can say is f plus n, but maybe is also g plus n. Okay, so here f and g are both equivalent. So I can pick f equals to g plus on n, where n is a function with semi-norm equals to 0. Okay. So I can, when I make this definition, I can use f as the representative, and I define it as the semi-norm. I should put the semi-norm here, the semi-norm of f, or I can use the semi-norm of g. So to show it's well defined, I basically need to show f and g have the same semi-norm. All right, so one direction is fairly simple. So if I do the semi-norm of f, okay, so by triangle inequality, I have this is less than or equals to the semi-norm of g plus the semi-norm of 0, but semi-norm of 0 is equal to 0, so it's bounded above by the semi-norm of g, okay? So on the other direction, well, you can really do something similar. So you can say, well, here g is equals to f minus n, so the semi-norm of g is less than or equals to the semi-norm of f plus the semi-norm of minus n, but minus n you can pull out the absolute value of 1 out there, but in any case, this one still has equal to 0. So on the other hand, you have the semi-norm of f bounded below by the semi-norm of g. Okay, so they have to be equal. Okay, so in other words, this definition, this norm of f, f tilde, the equivalence class, is well defined. Okay, so let's just say it's well defined. All right, because it's well defined, so now let's check is in fact a norm. Okay, so to show is actually a norm is fairly simple. So first of all, the equivalence class of 0 is equal to 0 because it's just equals to the semi-norm of 0. So for the scalar multiplication, so let's consider some alpha f, the whole thing tilde. Okay. So by definition, this is just, I pick one representative, so I can just simply take alpha f, okay, that's the semi-norm of that. And I can pull out the alpha outside, and I have the semi-norm of f. And now the semi-norm of f is just equal to the f tilde, okay? So this is what we have, okay? And you can kind of convince yourself this one is essentially the alpha times the f tilde, okay? That's how we define a quotient vector space. All right, and the triangle inequality follows really similarly. You have the equivalence class of f plus g. By definition is f plus g, the semi-norm. Triangle inequality tells you this is bounded above by the sum of their semi-norm. And on the right-hand side, you can say, well, the first one is just the equivalence class of f, the norm of that, and the equivalence class of g, the norm of that. Okay, and again, this the equivalence class of f plus g is just the equivalence class of f plus equivalence class of g. Okay, so you prove the triangle inequality. All right, and finally, to show its norm, we need to show if it's equal to 0, then the whole thing has to be equal to 0. But here, so if f tilde is equal to 0, it's just equivalent to the semi-norm of f is equal to 0, while that's equivalent to f is inside the kernel, or inside this linear space N. Okay, and because it's in N, it's just equivalent to the 0 function. So f is equivalent to 0, so this f tilde is just the 0 tilde. Okay, so they're the 0 equivalence class, or the 0 vector. Okay, so you always have a normed vector space. Okay, so this is what we proved. Okay. All right, so now, so we are given this space L1 of mu. Okay, so this is all the, so I should have a break. So here, this is all the f that's integrable on these this measured space. Okay, so and we show that the one norm is a semi-norm. Okay, so this from the last video. So automatically we can identify what is kernel. So its kernel is basically all the f which has measured the semi-norm one norm equal to 0. So is, you can say this is essentially all the f such that f is equal to 0 almost everywhere mu. Okay, we proved this from the last video. So this N is a vector space from what we saw in this class. And this will put the L1 of mu, if you quotient out this N, let's give it another name. So let's use a curly L of 1, okay? So this one will be a normed vector space, okay? It's a normed vector space. Okay, you basically treat two functions are the same if they're the same almost everywhere, okay? So this is the L1 of mu, okay? So L1 of mu consists of equivalence class, or you can just pretend it's just a function in L1, but two functions are the same if they're almost everywhere the same, okay? So the norm on this L1 of mu, right now we abuse our notation, so this is just, I define the f tilde of 1. I'll just define it as the one norm as in the L1 without the on the semi-norm L1. Okay, so this is the standard notation. Okay, so later on, I usually, when the context is clear, I will remove this tilde. So the one norm on this L1 space is just the one norm on the other L1 space. Okay, the curly L1 and the L1, they have the same norm. But on the curly L1, you really have a norm. The other one is just a semi-norm. Okay. Well, now, so we're happy. So we have a normed vector space. So what's next? Okay. So if it's a norm vector space, sometimes we like to have ask whether this norm vector space is complete. Okay, because if it's complete, then every Cauchy sequence converges to something inside this L1. And this is the next big theorem we're going to show. So in the next video, in the last part of this lecture, we're going to show that this L1 of mu is complete. Okay, so let's put as a fact here, is complete. And the proof, that's where we actually need to use some limit theorem of these L1 functions, and that's where we need the Lebesgue dominated convergence.